An ideal gas undergoes four different processes from the same initial state as shown in the figure. Those processes are adiabatic, isothermal, isobaric, and isochoric. So we have this P, pressure versus volume graph for an ideal gas, and it is going four different processes starting from the same position or the same state, right? So from this state, the gas is undergoing, so obviously this is what? Isobaric. The pressure is constant for this process, okay? This one is isochoric, right? The volume is fixed at this volume, okay? So obviously we don't have confusion in 1 and 4, but out of 2 and 3, we have to guess which one is isothermal and which one is adiabatic, okay? So there are two ways of looking or solving the question. One way is like, by looking and analyzing, like we know the first law of thermodynamics. So using that we can solve it, and I'll also tell you the analytical way, like using formula, how we can find out. So first let's see how we can, just by looking at it and what is happening, we can figure out which one is which, okay? So this is this is part 3 and this is part 2. Which one is adiabatic? And so we know from the first law, what do we know? That Q, if you give heat Q to a gas, a part of it changes the internal energy and a part of it goes into doing some work, right? Okay. Q is equal to delta U plus, and both the gases, if you see, they are going from left to right. Both of the gases are expanding. Okay. So the gases are expanding. That means they are doing positive work. For both of them, the gas is doing some positive work. So whenever the gas does some positive work, if it is adiabatic, that positive work is going to be at the expense of its internal energy, right? Fine. And the temperature of the gas is directly proportional to the internal energy. The internal energy of the gas is directly related with the temperature. Higher the internal energy, higher the temperature. Lower is the temperature, lower is the internal energy. Okay. So now you see, for the isothermal, the temperature will not be changing, right? For the isothermic one, the temperature will not be changing, right? So whatever was the initial temperature, for both the processes, the initial temperature is the same, and for isothermal, the temperature is going to be the same what it was initially. But adiabatic, you are not supplying any heat from outside. So it is going to do some work, that is positive work here, at the expense of its internal energy. That means the internal energy will be reduced for the adiabatic one. That means the temperature is going to be lower finally for the adiabatic one, isn't it? So which one? 0.3 and 0.2. Which one do you think for the given volume has a lower temperature, right? We can use PV is equal to nRT, right? So T is PV upon nR, right? Now you see here, for the same volume, for this volume, right, nR, n into R is constant. So higher the pressure, higher the temperature. So obviously this temperature 3 is more than the temperature of the 0.2. That means 0.2 is at a lower temperature. That means that is going to be for the adiabatic one, right? So by looking at it without using any formula or anything like, doing differentiation or anything, we can straight away say that the path 2 is going to be adiabatic, okay, by this logic. So this was, using the first law and then commenting on the paths, okay. We had another way also, okay. We have the expression for, adiabatic and isothermal, so we can use that and, analyze the situation analytically also, okay. So let's look at that also. So we know that for adiabatic processes, PV to the power gamma is constant, or let's say K, constant K1, let's say some constant K1, okay. So this is for adiabatic, and for isothermal what happens? PV is equal to nRT, T is constant, so this is another constant. So this is for isothermal, right? For isothermal, P times V is constant. For adiabatic, PV to the power gamma is constant, okay. And gamma is what? Gamma is Cp upon Cv. That is more than 1, we know, okay. Gamma is more than 1. Cp upon Cv is more than 1 because Cp is more than Cv. right? So now you can, we'll try to find out the path by seeing the slope, okay? By seeing the slope of the curve, okay? So if I, try to write the slope for this one, if I try to differentiate this one on both the sides, what will I get? Use the product rule. So you're going to get, I differentiate with V, volume, on both the sides. So you'll get V to the power gamma dP upon dV plus P times gamma V to the power minus 1, V to the power gamma minus 1 is equal to 0. On the right hand side, that's a constant. If you differentiate, it's going to be 0, right? So from here, you say that dP upon dV, if you solve this, so dP upon dV is going to be minus gamma P upon V, okay? So this is the slope. dP upon dV will give you the slope. So this is for adiabatic, okay? For the slope for the adiabatic curve, right? And similarly, if I try to find out for the isothermal one here, I differentiate both the sides. So I'll get P plus V dP upon dV is 0 on the right hand side. That's just a constant. You differentiate, it will become 0. So dP upon dV, the slope here is going to be minus P upon V, right? So see, for both, so this is the isothermal one. This is the isothermal one. The green one is the adiabatic one, okay? So now see, both the curve, both the slopes are negative, okay? Negative. Whenever a line is, leaning toward the left like this, the slope of the line is negative, okay? Whenever the line is like this, leaning toward the right, the slope of the line is positive, okay? That's what we know already. So both the slopes, if I, make a tangent to the curve, okay, at any point like this, okay? So now see, both the tangents have negative slopes, but which one is more slant? The inclination for which one is more? Okay, obviously the second one, right? The second one, I'll make, better tangent like this. So you see, the slope on the line 2 is steeper. It is steeper, right? And this one is not so steep on that one, on the curve number 3, right? That means magnitude wise, the slope on curve number 2 is more, okay? So that has to be adiabatic, because we see that this thing here is more magnitude wise. This is going to be more than the isothermal one. So the slope of adiabatic, why? Because this gamma is more than 1, right? This gamma is more than 1. So gamma times P by V is going to be more than P by V. So the magnitude wise slope of the adiabatic one is going to be more, right? And I can see here that the tangent that you have drawn on curve 2 has more slope, okay? It is steeper than the one on curve 3. So from there we can straight away say that, okay, the curve number 2 is going to be adiabatic, okay? And the curve number 3 is going to be isothermal. So that was another way to comment or get the answer for this question, okay? Any way, either the first way or the second way, whichever one you think is better or easier, you can use that, okay? I hope you got the answer. Thank you.